So just as a little reminder from last week, we discussed classical optimization problems, and in particular the example of the max cut problem. And I don't want to repeat the details here, but we said that many of these optimization problems are classically hard in the sense that solving them requires resources that scale exponentially with the size of the problem, in this case the number of nodes in the graph. And we discussed that we can map this problem to a problem regarding qubits. If we identify the nodes in the graph with qubits, then we can, and in each cut we separate the nodes into two subgroups, and the nodes in one subgroup we labeled +1, the other we labeled -1. We introduced the variable z and gave it the value +1 in one group, -1 in the other. We can map that to basis states of our qubits. In the standard basis states 0 and 1. And then we discussed the fact that the optimization problem, the classical optimization problem, amounts to the minimization of a certain cost function, which is a function of these variables z. And we discussed that we can map this cost function to a Hamiltonian of our qubits. And thus the problem of minimizing the cost function becomes a problem of minimizing the expectation value of the Hamiltonian. In other words, finding the ground state of that Hamiltonian. Yeah, so many, not all of course, but many classical optimization problems can be mapped to the problem of finding the ground state of an assembly of qubits. Furthermore, we discussed last week a problem that often arises in quantum chemistry, namely that you seek the ground state of a molecule. And we discussed the fact that this too classically is a hard problem, scales exponentially with the number of electrons in the molecule. And we discussed that this kind of problem too can be mapped to a problem regarding qubits. Namely, we identify or we associate with each orbital, that is single electron basis state in the molecule, we associate with any such orbital a qubit. And due to the Pauli principle, each orbital is either occupied or empty. And with these two possibilities, we associate the basis states 0 and 1 of our qubits. And then, just as in the case of classical optimization, the many electron Hamiltonian, of which we want to find the ground state. So we want to minimize the expectation value of that many electron Hamiltonian. We can map that to a Hamiltonian of our qubits. And we have to minimize the expectation value of that Hamiltonian for our qubits. This map is not a trivial affair, and I didn't talk about the techniques for doing that, and I won't do that today. I just wanted to sketch the basic idea that you can map the one problem to the other problem for qubits. And this shall be the starting point for today, that we assume that whatever was our starting problem, we have succeeded in mapping it to a problem for qubits. And we have a Hamiltonian for our qubits, and we want to find the ground state of that Hamiltonian. So that shall be today's starting point. And to begin with, I would like to make a few remarks about qubit Hamiltonians. So we are talking about some assembly of n qubits with a Hamiltonian. What is the most general form of such a n qubit Hamiltonian? For a single qubit, in single qubit Hilbert space, if you consider an arbitrary observable for a single qubit, in the standard basis that is represented by a Hermitian 2x2 matrix. A Hermitian 2x2 matrix is specified by 4 real numbers, so 4 real parameters. And the sum of 2 Hermitian operators is again a Hermitian operator. And when you multiply a Hermitian operator with a real number, the result is again a Hermitian operator. For this reason, or for these reasons, Hermitian operators for a single qubit form themselves a linear space, a real linear space of dimension 4. It's a 4-dimensional real linear space. And this real linear space of Hermitian operators has a basis. That basis must comprise 4 Hermitian operators, which are linearly independent. And it turns out one particular basis is comprised of the 3 Pauli operators plus the unit matrix. So any Hermitian operator, and therefore any observable of a single qubit, can always be written as a real linear combination of the 3 Pauli operators and the unit operator. And this finding can be generalized to many qubits. If you have n qubits described in an n qubit Hilbert space, then an arbitrary observable in that many qubit Hilbert space can again be written as a real linear combination, and in this case now of tensor products of Pauli operators and unit operators. And this applies in particular to the Hamiltonian. And this formula shows this general form. So any Hamiltonian can be written as a linear combination, that's the sum, with real coefficients. This is the little h. And then tensor products of sigmas, and these sigmas here are either Pauli operators. So when the index mu is 1, 2, or 3, then it's one of the Pauli operators, or sigma 0 is defined as the unit operator. So the Greek indices, they run from 0 to 3, and the sigma mu's are either the unit operator or one of the Pauli operators. And so here you have arbitrary tensor products of these sigmas, and as I said before, any observable and any Hamiltonian in particular can be written as a real linear combination of these tensor products of these sigmas. And these tensor products of sigmas, so of unit operators and Pauli operators, they constitute a basis in the real linear space of observables for n qubits. And this particular basis is called the Pauli basis. It's the Pauli basis in the space of observables. Let me give you a specific example. So here is a Hamiltonian for 2 qubits, or to be more precise, its matrix representation in the standard basis in the Hilbert space of 2 qubits. And it has diagonal elements, A, B, C, D. And then it has some off-diagonal diagonal elements which all have the same value, E. And I claim that this Hamiltonian can be written as a real linear combination of tensor products of Pauli operators and unit operators. And indeed, I'm not going to prove this here. That's something that you can easily check for yourself. This particular Hamiltonian for 2 qubits can be written as a linear combination of unit tensor unit operator. That's the first term. Then unit operator tensor Pauli Z tensor unit operator, then a tensor product of 2 Pauli Z's and a tensor product of 2 Pauli X's. Pauli Y doesn't appear in this special case. With various coefficients which are real. So I'm assuming that also in the matrix, in the original matrix, these are all real. So the coefficients are real. And you can check for yourself that this is the correct representation of this particular Hamiltonian in the Pauli basis. So from now on, I would like to assume that we have our n-qubit Hamiltonian, whose ground state we want to find, given in the Pauli basis, in this particular form. Now, if we turn to the problem of finding the ground state, what does that mean? How can we approach that? We can look at various possible states of our n-qubits and calculate the expectation value of the Hamiltonian, the energy expectation value. And then we try out different states, we vary the states and try to find that particular one which minimizes the expectation value. When we have the Hamiltonian given in this standard form with the Pauli basis, then this opens a possibility, a path how we can determine the expectation value in a given many-qubit state in the following sense. So we want to determine, calculate or measure the energy expectation value, the expectation value of the Hamiltonian. If the Hamiltonian is given in this standard form with the Pauli basis, then determining the expectation value of the Hamiltonian amounts to determining the expectation values of these various tensor products of Pauli operators or unit operators. So in our particular example, this amounts to determining or measuring the expectation values of these various tensor products that I enclosed in yellow. And if we want to do this experimentally in a circuit, we know what we should do. We can do that by subjecting both qubits to a measurement in the standard basis. Yeah, for example, the standard basis is an eigenbasis of Pauli Z. Yeah, and therefore, I mean, in the first case, when we have the tensor product of two unit operators, we don't have to measure anything, of course. The expectation value is 1. If one of the two observables is the unit operator, then for that particular qubit, we don't have to measure anything either. We just have to measure then Pauli Z for the other qubit. And we do that in a circuit, we do that with a measurement device in the standard basis. And if we have the tensor product of two Pauli Z's, that's just a simultaneous measurement of Pauli Z that is in the standard basis on both qubits. So all the tensor products that I enclosed in yellow can be measured in circuit notation by our standard measurement devices. There remains in this particular example one more tensor product, namely the tensor product of the two Pauli X. Now the standard basis is not an eigenbasis of Pauli X. The eigenbasis of Pauli X, that's the plus minus basis. If you remember the representation of the Bloch sphere, then the two antipodes along the x-axis were the plus and minus states, and these are the eigenstates of Pauli X. So in order to measure Pauli X, we need a measurement device that measures along the x-axis of the Bloch sphere, and that is in the plus-minus basis. The plus-minus basis is rotated from the standard basis by means of a Hadamard transformation. So if before applying a standard measurement device, we insert a Hadamard gate, then effectively we are rotating the measurement axis. We rotate the measurement axis from the standard 0-1 basis to the plus-minus basis. And that rotated axis then measures Pauli X. So in a circuit, the little setup in green, in the green box, that allows us to measure the tensor product of two Pauli X's. So in this particular example, if we want to determine the energy expectation value of this Hamiltonian in a particular 2-qubit state psi, then what we can do is we can prepare the state psi and then send it through the measurement setup in the yellow box. And we do that, we repeat that, we do that several times until we have enough data. And this allows us to determine the expectation values of all the tensor products marked yellow. And then we prepare the same state again and send it several times through the measurement setup in the green box until we've collected enough data. And this allows us to determine the expectation value of the tensor product marked green. So Pauli X times Pauli X. Yeah. So the problem of determining experimentally the expectation value of this 2-qubit Hamiltonian in an arbitrary 2-qubit state psi has been mapped to a circuit where we apply standard measuring devices for qubits, either in the original standard basis or in some rotated basis, and we can achieve the rotation of the measurement basis by adding Hadamard gates in this example. If we had Pauli Y's as well, then we would have to use a different rotation for the basis. Yeah? But so we can translate this measurement procedure into our language of quantum circuits.